GD&T is a language of symbols used to communicate design intent. Now I've identified 4 major concepts that I'm going to cover in this video that's going to help you with your GD&T studies. The concepts are 1, datums, 2, feature control frames, 3, material condition modifiers, and 4, basic dimensions. If you know what these are, you can identify them and you can apply them to a drawing. You're going to have a pretty good handle on how the system works. Let's get started right away with datums. Now, the definition of a datum is that it is a theoretical point, line, or plane. Now, we can't touch or measure something that's theoretical, so we identify features on the part to serve as datums and simulate them with datum feature simulators, which are just inspection equipment. Whether it's a surface plate to simulate a plane or a gauge pen to simulate a cylinder, we're just going to get as close as we can to that theoretical perfect datum. Now, the other way to understand datums, which is very, very important, is that datums are places to measure from. Let me give you some examples of what I mean on the board. So I've got 2 drawings on the board. Let's talk about this one first. We've got a stepped block with a leader directed note that indicates parallel to 5 thousandths. Now, this is definitely not allowed anymore, but if you look at drawings that are 50, 80 years old, you might see something like this. This is what's known as an implied datum. It's up to whoever is interpreting the drawing to decide what this surface is supposed to be parallel to. Now, you might say, duh, it's this large surface down here, and you'd probably be correct. But somebody else could say, hey, I know how this part functions. It actually fits upside down. That surface is supposed to be parallel to that surface, right? So what datums do is specify exactly which surface something is supposed to be oriented to or located from. Let's go into our next example. We've got a block with a hole in it. Now, we've got a center line going through the block and then 1 dimension covering the height. This indicates that that hole is centered in the middle of the block, okay? So that center line and then that dimension indicates this. We don't need another dimension for the location of that hole. But one person could say, let's measure from this surface, make it 1 inch plus or minus 10 thousandths. Another person might say 1 inch plus or minus 10 thousandths from that surface. Another person might say, well, why don't we take the block and put it in a vise and then find the center, right? Simulate that center line and then get the location from there. Now, none of them are really correct, right? Plus or minus dimensioning really doesn't have rules for how to do this stuff. You're leaving the interpretation up to whoever has the drawing, who's making the part, who's inspecting the part. What datums do, we can identify this is a datum and clearly state that the center of this part is a center plane datum and then the hole is located from the center of the part. It's all about being explicit about the drawing requirements. Now, we'll talk more about datums as we go through this talk right now, but this is good enough for now. Datums are places to measure from. Next up, let's talk about feature control frames. Now, this example here, I've just written it out in a note, and that was the way to do it. Older drafting manuals would just spell things out. Hey, make this cylinder concentric to this cylinder. Make the total indicator read out this. Everything was written in notes. The problem with notes is that it leaves room for interpretation. Think about if you ever took an English class and you're reading an essay, your teacher expects you to interpret it, but they know every student isn't going to interpret it the exact same way. So notes should be as short as possible. That reduces the room for interpretation. But if we can use symbols instead, we further reduce the room for interpretation. So to make this into a proper GD&T callout, we're going to use the feature control frame. So feature control frame is a box. In this case, it's leader directed. The very first box will have the geometric characteristic symbol. The next one will have the tolerance. After the tolerance will be the datums. In this case, with this particular tolerance, we only need one datum. We're going to write our datum feature symbol down here, connect it to the bottom surface. So now it's explicit what the drawing requirements are. Okay? So next up, let's talk about feature control frames. Now I've replaced the note on this drawing with a feature control frame that accomplishes the same thing. The first symbol is the geometric characteristic symbol, then their tolerance, then our datum references. In this case, we're just saying that this surface is parallel to 5 thousandths to datum A, which is this bottom surface identified with the datum feature symbol. Now, let's move on to a couple more examples of feature control frames. So feature control frames differ depending on how they're applied, what geometric characteristic is applying, and how many datums there are. Now, there's more videos I've made about this, specifically the different kinds of geometric characteristic symbols, but let's just talk about a few. First is form tolerances, like flatness, typically don't or never have a datum reference. Because form tolerances only apply to individual features, there's never a need to relate them to anything else. So in this case, a flatness tolerance is directed with a leader to a surface. It's just saying that surface is flat to within 10 thousandths. Next up, we've got a profile, which is very tricky. Profile can do a lot of different things. It can function just like flatness, or it can locate surfaces. In this case, a datum reference to datum A, it's doing the job of flatness, parallelism, and locating a surface if we have a basic dimension. And then another form tolerance, straightness, applied to the surface of a cylinder. This controls the line elements around the cylinder. Very simple feature control frame, just a symbol and then a tolerance. Okay? So let's talk about something a little bit more complicated. We'll get into position, which generally have the most complicated feature control frames. So allow us to talk about all of the elements of the feature control frame. So here is about as complicated as a feature control frame can get, but it's not too bad. So we've got a block with a hole in it. We've got basic dimensions locating the center of the whole feature. We've got 3 datums, so A, B, and C on perpendicular surfaces of the part. We're leader directed to a size dimension. Now, position is almost always applied with a directly toleranced dimension that applies to a feature of size. A feature of size, real quick, is something you can measure with opposing points. So this width of the block we can measure with opposing points. This hole we can measure with opposing points. Okay, so quick definition of feature of size. So our feature control frame, like I mentioned, the first block is the geometric characteristic symbol. The next block is the tolerance and associated adjectives to the tolerance. So in this case, with position, we have a diameter symbol here to indicate that the tolerance zone is a cylinder. So you can imagine there's a cylinder centered where these basic dimensions terminate of 30 thousandths. That's where the axis of this hole must lie. Next, we have a material condition modifier. In this case, it is MMC. This just means that as this hole gets larger, more locational or positional tolerance is allowed. And I'll put a card up. I made a whole other video about it. We'll just gloss over it for now. Next, now this is important, are datum references. Most of the time, they will be written A, B, C because it's a popular choice for designers. It makes it easy to read drawings because people are used to seeing it. It does not have to be A, B, C. It's in the order that the part is set up for inspection. So datum A should be a mating surface, the largest and most important mating surface. Normally, for a block like this, it would be one of the largest planes, right? That gives you good repeatability for inspection. Doesn't have to be. The second one is our secondary datum, typically the second largest surface, but it can be other kinds of features as well. It could be a feature of size, like a slot or a cylinder. So we could switch this. It could just as easily be ACB. In this case, we'd set up to A, B, and then C, okay? So they are in order, and it does matter. It's known as primary, secondary, and tertiary. Some people know this as the 3-2-1 rule. So 3 points for the primary, 2 points for the secondary, 1 point for the tertiary. The idea is to completely immobilize the part in all 6 degrees of freedom when you're inspecting it, right? It's stated on the drawing exactly how it's supposed to be set up for inspection. Again, this reduces errors in interpretation if everybody is trained up on how to apply and interpret GD&T. So now let's move on to material condition modifiers. This seems to throw people for a loop, but it's a simple system when you look at it. We've got 3 material condition modifiers to worry about. MMC with its little M with a circle, or written MMC, or spelled out as maximum material condition. Next is LMC, L with a circle, or LMC, spelled out it is least material condition. And then I put the symbol here. It's an S with a circle. Currently, the symbol is not used, and it has not been used since the ASME Y145 1982. But some people still, are comfortable with this symbol in notes and things. So it's spelled out as RFS. We've talked a little bit in previous videos about the concept of MMC. It simply states that external features at their maximum material condition are at their largest size. So if you have a pen that's plus or minus 40 thousandths, the MMC is 1.04, the largest pen. It's the opposite for internal features. So if you have a hole at MMC, it's the smallest the hole is allowed to be within the limits of size. It's a great way to compare whether parts will fit and how much allowance is between them. Another way to think of it is that the MMC is the heaviest part. So the largest pin is the heaviest pin. The smallest hole creates a heavier part than having a larger hole. Now, LMC is the opposite. So the LMC of a pin is the smallest it's allowed to be. The LMC of a hole is the largest it's allowed to be. We generally split these up into internal and external features. So the pin would be our external feature. Whether it's a pin, a block, or anything else, it's external. Internal could be a slot or a hole or a groove or any number of different kinds of features. RFS does not have a symbol because it is the default requirement for feature control frames applied to features of size. So what's a feature of size? I talked about it a little bit before. Let's go in a little bit more depth. A feature of size is something with opposable points that can be measured. So let me give you some examples. If you have a block, the width dimension, that is a feature of size. If you have a pin with a diameter dimension, that's also a feature of size. It can be measured with 2 points. Same thing with a slot or a groove. That would be a feature of size because you can measure it with 2 opposing points. So think about a caliper, the inside measuring part of a caliper. What is not a feature of size is something like this radius, right? You can't get 2 points on that radius. Now you could make an argument that, okay, if the center line is the radius is on the same plane as the top of this part, you could. The problem is you got a tolerance on that radius. So if the radius comes in small, then you can't get 2 points. If it comes in large, maybe you can, but you wouldn't want to call that a feature of size. Next, something like a chamfer, not a feature of size because you can't measure out into air with two opposing points. Same thing with this open cut right here. That would not be a feature of size. So it's important to understand what is and isn't a feature of size to know what material condition it can apply at. So things that are not features of size cannot have material conditions. You can never have more or less tolerance than stated for something that isn't a feature of size. Now, let's talk a little bit about what these symbols do in practice. So, I've got a pin with a size dimension and a straightness tolerance applied to the derived median line. This just means, real quick, that the center of that pin must lie within a cylinder that is 20 thousandths in diameter, and that's all we'll worry about for now. So, there's no MMC or LMC symbol, but it is a feature of size. In that case, regardless of feature size, the one where we don't use the symbol applies. It is the default requirement. This is known as rule number 2 in the ASME standard. So all that means is that no matter what size this pin comes in at, there's always 20 thousandths of geometric tolerance. So pretty straightforward, right? It's exactly what you'd think it would be. Now, let's try the MMC modifier. So if this tolerance applies at MMC, it's best read as that it applies only at MMC. 20 thousandths only at MMC. So let's write that right here. When the pin comes in at 1.02, the MMC of this size, 20 thousandths of tolerance is allowed. But if the pin comes in toward its LMC, so it comes in smaller, more geometric tolerance is allowed equal to the difference, the MMC to the actual size. All that means, if it comes in 10 thousandths smaller, you get 10 thousandths more geometric tolerance. Simple enough, right? Same thing, we just keep going down the list. If the pin comes in at its LMC, you're allowed 60 thousandths of geometric tolerance. That's also equal to the total size tolerance, 40 thousandths, right? So we just add 40 thousandths to the 20 thousandths to see the total amount of geometric tolerance that may result if the pin comes in toward its LMC, okay? So let's try the LMC modifier instead of the MMC modifier. So now we read this, so we have 20 thousandths of geometric tolerance only at LMC. So we'll reflect that right here. If the pin comes in toward its MMC, you get more tolerance equal to the difference. So if the pin comes in at 0.99, you get 30 thousandths, 1.0, you get 40, and so on. So LMC is just the reverse of MMC in this situation, okay? So RFS is default for geometric tolerances applied to features of size. MMC and LMC can be used to allow more tolerance depending on the actual size the part comes in at, okay? Let's move to another concept, which might be a little advanced for a video like this, but let's go ahead and tackle it. Let's talk about datum feature material boundaries. These are known as MMB, LMB, and RMB, which sound a little like, MMC, LMC, and RFS. They're the same thing, but they're for the datums. So let me get this drawn up on the board. So I've got a drawing on the board here. We've got a donut shape with 2 dimensions applied to it. The outside diameter is identified as a datum with a size tolerance 2 inches plus or minus 20 thousandths. The MMC of that feature is 2.02, the largest it can be. We've got an internal diameter with a size tolerance and a position tolerance. So we're positioning the smaller hole to the outer diameter. The feature control frame, position, diameter tolerance zone, 0 at MMC. This just means that if the hole comes in at its smallest size, it has 0 positional tolerance. But if the hole comes in any bigger, you get more positional tolerance, just kind of like the chart we were doing before. Datum A is our primary datum, so we've got to establish 3 points of contact with datum A here. But datum B applies at maximum material condition, or MMB, maximum material boundary. What this is an optional inspection technique. You don't have to do this. You could inspect it with a closing shape, just like an RFS inspection. But you could also measure it with a fixed gauge. So what this is saying is that you can check it at the MMC or virtual condition of this feature. So the MMC is 2.02. You can make a gauge for this part and check it that way, right? You're saying the inspection here is fixed. So what would the gauge look like? The gauge would be a ring with a pin in the middle, the ring to simulate datum B at its MMC, so it would be set to 2.02 inches, the maximum material boundary. The pin would be set to the MMC of this feature, so 1 inch plus or minus 20 thousandths. We would simulate it at 0.98. So if the part fits in that gauge, we've established that it has not violated this boundary. Okay, now all we'd have to do is check and make sure the hole wasn't too big. Okay? So these aren't always used, but they are a technique to save, money at inspection. If you can set your dimension or your tolerances like this, you can automate inspection to a pretty serious degree, right? You could have a robot drop this washer, this donut, into a gauge, and if it fits, it's good. If it doesn't fit, it's bad. It goes in a different bucket, okay? So that is a brief introduction to material condition modifiers. Next, we'll move to basic dimensions, which is mercifully simple, and it'll be the last thing I talk about in this video. So basic dimensions are theoretically exact dimension values applied to size or location of features that are controlled with a feature control frame. It's very important that basic dimensions are associated with a feature control frame. So in this case, I've just given the left-right basic dimensions, but these basic dimensions show you where the tolerance zone should be for this position tolerance. Another example are things like profile that control the location of surfaces with basic dimensions. Now, since basic dimensions are theoretically perfect, they don't count in a tolerance stack up. So they can be written differently than plus or minus dimensions. So if you did a plus or minus dimension like this, you could have a lot of stack up. With basic dimensions, as long as they connect together, you can interpret them. You can interpret the distance from the centers of the holes as 1 inch. Okay. Now, at inspection, you really shouldn't indicate the tolerance or the actual dimension for basic dimensions. Okay, so all of these dimensions here are associated with either this position or this profile. That's where the tolerance for the basic dimensions is. And the last thing about basic dimensions is that they must come from datums. That's where you're measuring from. The basic dimensions have to lead back to datums. Now they can loop. So datum C is here. We can go 2 inches and then back and then locate this, but they've got to be connected. Okay. So that's it for this video. I just wanted to go over these 4 major concepts of GD&T. I hope you got something out of it. If you enjoyed the video, please like and subscribe. Leave a comment down below and stay tuned for more videos like this coming soon.